In previous lecture connectivity topic, I already discussed path. Path is a sequence of edges by which we can traverse source vertex till end vertex, and when source vertex and end vertex are same, it's called as a circuit or cycle. I also discussed path for directed graph and what is connected graph and disconnected graph. If there is a path between every pair of vertices, it's called as connected graph, and if it is not connected, it's called as a disconnected graph. And if the graph is disconnected, it's a union of connected component. Next is cut vertex or articulation point. If removal of a vertex make the connected graph disconnected, it's called as a cut vertex or articulation point. I already discussed all this. Next I will discuss cut edges. If removal of a edge make the graph disconnected, it's called as a cut edge or bridge. If removal of vertex make the graph disconnected, it's cut vertex or articulation point. If removal of a edge make the graph disconnected, it's cut edge or bridge. Next, example 4. Find the cut vertices and cut edges in the graph G1 shown in the figure. This is G1 graph. Here C can be a cut vertex. If we remove C and its all adjacent edge, then A, B, D will be one connected component. E, F, G, H will be another connected component. So removal of C divided this graph into two connected component. So like C is also a cut vertex, even B is also a cut vertex. So here cut vertices are B, C and E, whose removal make the graph disconnect. Next is cut edges. If we remove CE, then this part A, B, C, D will be one connected component. F, G, H, E will be another connected component. So CE is a cut edges. Like CE, AB is also a cut edges. If we remove ABH, A will be one connected component. Then B, C, D, E, F, G, H will be another connected component. So here CE and AB are the cut edges whose removal make the graph disconnect. Next is vertex connectivity. Not all graph have the cut vertices. Some graph have no cut vertex. For example, complete graph. If Kn is a complete graph, there are no cut vertex. If I remove a vertex and its adjacent edge, it will create another complete graph of size n-1. Okay, if Kn is a complete graph, after removal of one vertex, it will be Kn-1, but it's complete. Okay, so it is not disconnecting. So a graph without cut vertices called as non-separable graph, means we cannot disconnect that graph. There are no cut vertex. But in that case, there may be set of vertices whose removal make the graph disconnected. So a subset of vertices whose removal make the graph disconnect is called as vertex cut, and minimum number of vertices in the vertex cut is called as vertex connectivity. So the vertex connectivity of a non-complete graph denoted by Kg is the minimum number of vertices in the vertex cut. Clear the difference? Cut vertex means single vertex whose removal make the graph disconnect. Vertex cut means group of vertices whose removal make the graph disconnect. And vertex connectivity means it's the minimum number of vertices in a vertex cut. A graph is K connected, or we can say K vertex connected if K of G is greater than equals to K. We can say one connected if it is connected and not a graph containing single vertex, means it have 2 or 3 vertex, means there is a vertex cut having one vertex. Next, a graph is 2 connected or bi-connected if it is non-separable and has at least 3 vertices, and removal of 2 vertices will disconnect the graph, means there is a vertex cut of size 2. If G is a K connected graph, G is a J connected graph for all J with 0 less than equals to J less than equals to K, means you can say if a graph is 3 connected, it's also 1 connected or 2 connected, means that J value can be lies between 0 and K. Now example 5, find the vertex connectivity for each of the graph in the figure. These are the graph. There are 5 graph. We need to find vertex connectivity for each graph. You can see all graphs are connected and all have vertices more than one. So all have the positive vertex connectivity. Now check G1 graph. In G1 graph, B is a cut vertex, C is a cut vertex, E is a cut vertex. As cut vertex are present, hence it is 1 connected. K of G1 equals to 1. Removal of one vertex will make this graph disconnected. We can say vertex connectivity is 1. Next, G2. In G2 graph, C is a cut vertex whose removal make the graph disconnected. Hence, K of G2 also 1. In G3, there are no cut vertex. Removal of any single vertex will not make this graph disconnected. We need to remove two vertex. Either you can remove BG. If you are removing BG, this part will be one connected component, this part will be another connected component. Or you can remove C and F. So DE will be one connected component, A, B, G will be another connected component. So there are two vertex whose removal make the graph disconnected. It can be BG or CF. That's why K of G3 equals to 2. Set of two vertex removal will make the graph disconnected. So it's a two connected graph, or you can say vertex connectivity equals to 2. Next, G4. In case of G4, if you are removing C and F, then it will make the graph disconnected. Hence, K of G4 equals to 2. It's a two connected or biconnected graph. Removal of two vertex make this graph disconnected. In G5, there are no two vertex whose removal will make this graph disconnected, but we can remove three vertex, like we can remove B, C and F. When we are removing B, C, F, it will make the graph disconnected. That's why K of G5 equals to 3. It's a 3 connected graph. In today's lecture, I discussed chord vertex or articulation point, chord edge or bridge, and vertex chord, vertex connectivity. In next lecture, I will discuss edge connectivity. If this lecture is helpful for you, please like, share and subscribe. Thank you.